What I want to do today is finish our discussion of these HEMTs that we started last time, high electron mobility transistors. And today we'll specifically look at one of the kind of the more popular 3-5 or compound semiconductor HEMTs that has generated a lot of interest, and also quite a few applications recently based on the wide bandgap gallium nitride based material systems. So we're going to look at the gallium nitride, some specifics of this particular 3-5 semiconductors that are different from the other 3-5s, which are gallium arsenide and antimonides that we have talked about earlier. So let's just look at, for example, one of the structures that we looked at in somewhat reasonable detail was based on either gallium arsenide or indium phosphide based materials, which are all 3-5s as well. And last class we are looking at kind of the reason why the devices are made the way they are, and we also spent some time looking at the this Poisson Schrodinger self-consistent solvers that are used heavily for designing these transistors. So we're going to actually start using, or rather we'll use a little bit of that today as well. Okay, so I'm going to just use it through the class today. So just to kind of summarize the 3-5s that we have looked at: gallium arsenide, indium phosphide, and I mentioned some details about the antimonide, or the 6.1 angstrom based materials, which have also a rich, very narrow band gaps and very high, very good transport properties, and also a rich range of band alignments, starting from straddling type 1 to staggered type 2 and type 3, which is the broken gap alignment. So there you can find them. Okay. So today, what I'll do is look a little bit more into the HEMT, and for example, if we design the material in a certain way, with a certain thickness of the barrier, with a certain doping density over there, what sort of, for example, a transistor, one of the most characteristic properties of a transistor is the threshold voltage, under which it's off and above which it's on. So that, for example, can be completely designed based on the material science of, for example, how thick is the barrier, what is the doping level, and all that. And so we're going to just do a little bit of that today, both analytically and just look at the self-consistent solution as well, and see that we can do quite a bit analytically, as a matter of fact. Okay? And then we'll kind of carry this over completely to gallium nitride based, and we'll discuss in a little bit of detail some of the material science and fundamental physical properties of gallium nitride that make it different from these materials. Okay, so before I proceed, any questions on what we have been discussing in the last class or a couple of classes before? Did everybody manage to download the software and install? So please do so. If you have any issues running it, please let me know, because well, the next assignment I'll give you a couple of problems where you kind of have to use it and get some practice with it as well. So, okay. Let's. What I want to start with today is I think kind of ran out of time last class, and want to just show that. Let's look at this particular structure we were looking at, for example, where all right, so let's see. Remember, this is one of the structures we looked at I said it's just kind of an optical design which has multi-layers of 50 angstrom, 5 nanometer of gallium arsenide on the top. And then you have kind of a, for example, you look into details, 100 angstrom of aluminum gallium arsenide with 30% aluminum, then aluminum gallium arsenide that's doped, gallium arsenide, and this thing repeats 3 times, and so on. So this was the detail. And what I showed in the last class was, I mean, as an example, the structure may be used for a separate confinement, and it's not necessarily like this is just a demonstration, but for example, if you want to confine light in some regions which has let's say the lower refractive index compared to the other regions, but you don't want the light to see a lot of puddles of electrons, then as an example, this could be used. I mean, this is not specifically for that purpose, because you see the width is only 10 nanometer, but the wavelength of light is generally much longer than 10 nanometer. But what I was trying to say is if you look at the carrier density, wherever the Fermi level goes into the bands, the carrier density is very high, right? This is the electron density in the conduction band. And when you see such a feature in any compound semiconductor device where you have a 0, 0, and then a very sharp increase, you know that this is a classical calculation, right? And then because what I mentioned in the last class, and also many times by now, is if you have a finite barrier width for electrons and you are doing your quantum mechanical problem correctly, then because of some penetration here and on the left side, the wave function penetrates, right? So therefore, it shouldn't be very sharp. There should be some electrons also in the barriers there, right? I mean, in the barrier layers. So so that for example, I don't quite know what I did wrong, but this, for example, you solve it by turning the Schrodinger's back on, right? This has been disabled at this stage, so kind of turn that back on, and let's run that now. Demo and optical. So it did calculate it, and so what I can do now is go back and try to replot this particular curve and see how the carrier density changed. Again, I mean, it will do what you expect to do, but just to look at how the modified carrier density looks now, so you can see it should really smoothen out, right? I mean, and it does. And the nice thing you see is now you can see that there is quite a bit of connection, electronically between two wells. So, right? So because of the penetration of the wave function on both sides, there is these electron populations seem like there's a strong connection, and they could potentially go across the barrier and all that kind of stuff. So. Okay, so now going back to the structure that we were looking at, the other structure we looked at last time was, let's say, I think I'm done with that, was this quantum well, right? And what I've done here is, let's look at the quantum well. This is something we well, okay, that's the one. Yeah. So you remember this one. So and you can make it calculate each and every eigenvalue in the well. For electrons, it found, for example, in this problem, it found there are 4 bound states, and for holes, there are light holes, heavy holes, and it found bound states for all of them. Right. So you can find them. You can plot the wave functions of each of these states. It's all available. But what I want to show now is basically this is a gallium arsenide layer of it's 15 nanometer, right? 100 to 250 angstrom. So that's 15 nanometer. And then you have aluminum gallium arsenide, 30%, right? So you see 30% here. 0.3 means 30% is aluminum. And what I've done is, so this is a total of 100 nanometer, but I've broken it up now into 3 layers. And what I'm going to do is I want to populate that quantum well with electrons. Right now, you look at this structure, there are very few electrons in the quantum. Basically, I mean, there are some, of course, I mean, but they're exponentially small. And you look at the carrier density is very low. Right? I want to put electron gas into that quantum well, and that will be the channel for the transistor. So going back again, so what I want to do now is create the HEMT. And if you remember, we had discussed the purpose of each of these layers in a HEMT in the last class. For example, looking at the which one were you talking about there? Let me just make sure. We looked at a particular structure. Yeah, this is the one we're looking at. You see, there's going to be N plus aluminum gallium arsenide and all that stuff. So we're going to just put dopants in, and what we could do is we can analytically calculate it and then compare it with what the model tells us. Okay, so just as an example, we start with so in the quantum well, what I'm going to do, right now there are no charges, so where would I put the dopants, right? That's the first question we need to bother about, right? So you can obviously put the dopants here in gallium arsenide, right? And that will ionize and you get the electrons there. And you will get electrons then, right? But I think, you can see generally what will happen is the electrons are in the same place as the ionized donor atoms, and it will scatter of them, and the mobility would be low. And the whole reason it's called a HEMT, or a high electron mobility transistor, is because the dopants are put in the barrier, right? And what happens then is if I put dopants in a barrier, and here's a quantum well, and I put the dopant atoms, say this is aluminum gallium arsenide, I replace some of the aluminum and gallium atoms with silicon, right? So either this or that. So silicon replaces some of these atoms, and it has one extra electron than either aluminum or gallium, which have 3 in the outermost orbit. And the end result of that is if I put dopants here, the dopant energy level, the electron energy level corresponding to the dopant, is a certain donor ionization energy below the conduction band edge. Okay? So that's the picture you have in mind. This is the conduction band edge, and the extra electron that's tied to the silicon is sitting here at this energy level, slightly below that. And typically the donor ionization energies would be just as an order of magnitude. You would like it to be smaller or of the order of room temperature KT. KT is 26 MeV. Why? Because then that electron that was tied to the silicon atom, because of the atomic vibrations at room temperature, it gets enough kinetic energy that it's kicked out into the conduction band. Thermally ionized. It's ionized. Okay? But now you can see that electron is not going to sit here, right? It's going to not wait here because the electron is delocalized. It's in a band. It can move around, but the moment it goes here, it's going to end up here. Right? And it's going to end up in the electron gas. So it's going to basically end up in the quantum well, and this is going to continue to happen. But as that happens, this gets positively charged, right? See, this is positively charged, and now there is electric field, because there's a positive charge, negative charge. There's electric field that develops in that direction, right? As this happens, so you dope even more, and you put more dopants here, more electrons here, and then the field goes up. So when the field is pointing to the right, you can see that whenever the field is pointing to the right, I release a negatively charged electron here. It wants to move to the left, right? And so what does it say about the band diagram? It says that the band is bending now because there's a field, right? And so what's going to happen now is as you dope it more and more, this band here is going to kind of bend like this, and you get, and the other thing is the field will be continuous across the junction, and what's going to happen is it's kind of going to start looking like that. Yeah. So the slope here and the slope here for gallium arsenide is going to be the same, but for gallium nitride, we'll see later, would be different. So there's a polarization charge as junction. Anyway, because we are going to put the positive charges here, and this is what is called modulation doping. And also, please read. I posted Herb Kroemer's article on where he describes the importance of this property. So you see the ionized donors are sitting here, but the electrons are kind of here in this quantum well, and they're separated physically by this distance, which you can call a spacer layer or something like that. And what happens is when you do the numbers, for example, if you look at transport properties for electrons moving in this direction, the mobility gets exponentially, meaning the scattering because of this ionized donors is exponentially damped based on how far you are from the electrons. So essentially, the mobility kind of goes up as a factor of something of this factor E, meaning the mobility or the scattering rate is damped by this factor. And here, let me just write that down. I'm not deriving it for you, but it looks something like this: 2 pi times the carrier density or the sheet density of electrons in units of per centimeter square, and we're going to calibrate ourselves. What are these numbers today? Yeah. We'll see that typically you're looking at about 10 to the power 12 per centimeter square electron density in a good transistor, and in nitrides you can get you can get about 10 to the power 13 per centimeter square, but that's the order of magnitude. 10 to the power 12, 10 to the power 13 per centimeter. So that's how many electrons we're looking for. And so what I'm saying is the Coulomb scattering rate 1 over Coulomb scattering, meaning due to impurities, gets damped by how far you are from the very strongly damped. Okay? And then that's kind of the reason you kind of get a higher mobility than normal structures. But then the truth of the matter really is at room temperature, the ionized impurity scattering is not the dominant one. The dominant one is just polar optical phonon scattering. We are going to discuss some aspects of this transport at a later part. Right now, we're going to just look at the electrostatics of the problem. How does this happen? So you can see these thicknesses and such things, the barrier thickness, the doping, how thick a layer you put the dopants in. All these are very critical because they determine very accurately what sort of stuff happens here. So what we can do is we put dopants in this layer, and that's kind of the reason why I've broken this up. You see, we had total of 100 angstroms of 30% algan here, but I've broken it up into, like, say 20, 50, and 30 now. This is one of the designs, not necessarily the only one, not necessarily the best one either, but I've broken it up because I want to put dopants in this middle layer here, over that 5 nanometer or 50 angstrom of 30%. And so I'm going to just put maybe a dopant of very high, let's say, 2E19 per centimeter cube, and then ask how does this thing change the band diagram, right? And then basically it's going to just do this. That's all, right? And what we're going to do now is let's run this run this code and see what is that, quantum well, right? All right, that was fast. So let's see, we can bring in the data and see quantum well. Okay, there you go. Yeah. So yeah, right. So you see, it did what we expected, right? But I mean, and you can see the electron gas now is, the quantum well is filled with electrons, right? You see, the density is, the volume density is reaching about 10 to the power 18 per centimeter cube. Now let's look at an interesting property of this structure. You can actually go back and look for what happened. Sorry, this screen is a little smaller than normal, but when I connect it. So what I want to check here is what is the sheet density of electrons in this well? How many per centimeter square total? What the plot showed you is kind of the volume density, right? And when you integrate, the area under the curve is the sheet density. Make sense? So that's the sheet density per centimeter square. What is the sheet density? So for that, you can kind of go here and look at the status file, because that gives you, that in every layer, how many electrons and how many holes do you have. Okay. So here's, for example, our quantum well layer, 15 nanometer of gallium arsenide, right? And you see it's saying that I have 2 times 10 to the power 12, roughly, 1.19 times 10 to the power 12 per centimeter square sheet carriers in that layer, integrated. Make sense? Yeah.
The sheets are like this way in the diagram.
Right. So let's see. So this is n of z, where z is this direction, but really this is a planar structure, right? So you actually have, kind of whole thing going in, and so the xy plane is the sheet. That's right. Xy plane is the sheet, and what we are, what it's telling us is the sheet density, that's, we can call it n sub s, is essentially just dz of n of z. That's all. It's integrated over the, not necessarily, I mean, this thickness is in the quantum well, but what you also see here is there are some electrons also in the barrier, right? And then this, I think you realize, is because this is a finite barrier, right? And there is a penetration of the electron wave function, and therefore you look at, though the barrier is sharply at 100 angstrom, the electron gas spreads out. It's not limited to 100 angstrom. There's a tail there, right? So that's it. So that's, and you can see there are some challenges immediately that if you dope it heavier, you will end up, if you dope it even heavier, you will at some point end up with electron gas here too, as the band. So that's called a parallel channel, and you don't typically want that, so because that will be low mobility channel now, right? Is sitting right, and so the band offset really limits how much electrons you can fill into the well, how much sheet charge you can get, because that's what determines that property. Now that's all fair and good. I mean, that's what your simulator told you. And by the way, yeah. So here's the other thing. In this quantum well, there is only one bound state. That's so electron eigenvalue. You see, it says there is. It has found one energy. Let me explain what this is. So when I draw the band diagram now accurately, let's kind of zoom in into this region, all right? And the Fermi level is kind of, let's say here. This is Fermi level. This is your conduction band profile, and it has gone below, and we just saw that here, right? Let's just up. Yeah. So you see, so this is the triangular well. Now the question is, how many bound states are there? So there are there are bound states in the well, but then there are also bound states below the Fermi level. The below the Fermi level ones are, ones are heavily occupied, because anything below the Fermi level, there are a lot of electrons there, and so what we are asking is, well, I know that from my quantum mechanical ideas that there is a ground state like that, then maybe an excited state E2, E3, and so on, right? But you can see that a very valid question is, how many bound states are there below the Fermi level, which are occupied of it clearly. I mean, these are also occupied, except they're in a Fermi tail. There are much less electrons. They're much less. But this is heavily occupied. A good way to reason it is, if I take this whole thing to 0 Kelvin, then how many subbands are going to be occupied? Does that make sense? Because attached to each of these is a subband. Remember, because of lateral motion, lateral free motion, attached to each of them is a subband. Right? So here, what we are seeing is there is only one energy below the Fermi level. So the following subband energies were found: E minus EF, and when E is below EF, it's negative. So, okay. And this is, how deep is it under EF? So it's saying, well, it's about 27, right? 2.7. So yeah, about 27 milli eV. This thing here is roughly 27 millielectron volts. That's what, at least this for the problem. Now from here you can kind of already estimate a few things. For example, if you have a subband, 2D subband, let me just recount. A 2D density of states happens to be effective mass by 2 pi h bar square times the spin degeneracy, which is 2. If you know the effective mass of the material that is, the quantum well is composed of, then that's the density of states times a unit step function E minus, E1 or whatever is your ground state. Remember, the density of states of a 2D system is, wherever your band starts, and then you have a unit step, right? Right? Do you remember that part? So, and this height is the density of states of a 2D electron gas. Now, because you know that the 2D density of states will look like that, and we're looking at gallium arsenide. Gallium arsenide has an effective mass of 0.067 roughly, right? Meaning times m naught, which is the free electron mass. So you can plug that in and say that, look, I have, just as a back of the envelope, I have 2e12 per centimeter square carriers in the well, and there's only one subband filled, right? So where is my Fermi level with respect to E1? So 1D Poisson and Schrodinger solver told you it's 27 MeV below, right? But can you do it analytically? And the answer is yes. It's very simple, right? What you do here is, you say this is the density of states, and if my Fermi level is here, right, then what are the electrons that are occupied? Let's look at low temperature for argument's sake. These are the electrons that are occupied, right? So the area there must be equal to 2e12 per centimeter square, right? And so that will tell you that so this quantity or in other words, the carrier density or the sheet density, I'm going to make it approximate now, reasonably close, is dE, density of states, and Fermi-Dirac distribution, but we are saying Fermi-Dirac, let's assume that it's a Chart function, we're looking at a low temperature, let's assume. Yeah. So what is that? Well, that's just this quantity m star over pi h bar squared times, you can see when you integrate it, you just get EF minus E1, where E1 is the ground state, right? Wherever the thing starts, right? So EF minus E1, and this is 2E12, and you can evaluate this. I'm not going to do that. You will get very close to this number, 27 MeV or something. Run that over. Okay? Yeah, just plug those quantities in here. Okay? So what you see is the carrier density. If you are filled only single subband fill, in each subband, the carrier density depends on linearly on how far you are from the Fermi level is from the minima, right? Linearly. This is not true for 3D systems, right? 3D system, you have a square root of energy, right? So it changes in a more polynomial kind of way, and in 1D system you have something like that, which changes differently. But in a 2D system, 2D electron gas with a parabolic dispersion, this is a nice little feature that the carrier density is going to change linearly with the Fermi in a subband. There are limitations to this approximation, especially when you go very high in this subband. It gets into non-parabolic regions and bands start curving over. I think you solved the current assignment where it's parabolic this way, but then it, but we are talking about not that level. I mean, we're not that high in the band. Any questions on this? Okay, so the second point I want to make is let's go back and look at what happened, because something looks a little fishy here. How many dopants did I put in, and how many electrons did I get? The electron density I got is roughly 2 times 10 to the power 12 per centimeter square in the 2D electron gas. Right? That's clear. We see that at least. I mean, we trust the program and all that. But how many dopants did I put in? Let's see. The dopants I put in were spread over this layer. So this is the dopant layer, right? Spread over 5 nanometers, right? And the doping density, so that's 5 nanometer, and the doping density is what? 2 times 10 to the power 19 per centimeter cube, right? So what is the total sheet density of dopants, right? So you see, so 10 to the power, all right, so 10 to the power 19 per centimeter cube times 5 nanometer, and it's centimeter cube, so let's just convert everything to centimeters. 5 nanometers is 5 times 10 to the power minus 7 centimeter, right? So the total sheet density of dopants, we can label it as N sub dopant, let's say, right, is, you can see it's about 10 to the power 13. Right? It's not about this, exactly right. So this is 10 to the power 13, but you only got 2E12 in the quantum well, right? So where are the other electrons? So where did they go? Any? Yeah. In the where? The barrier. So let's look at the band diagram. Yeah, right. So where are the other electrons then? So yeah, basically, kind of if you integrate the mobile electrons in the conduction band, here you got 2E12. The ionized dopant density is 1E13, but the whole thing must be charge neutral, right? So I have 1E13 positive charges here, 2E12 negative charges here. Where are the rest negative charges? So barrier meaning where? So meaning here into this. Let's see. So a very nice way to figure that out is look at the fields. So if your bands are bending linearly, that means there is no charge there. If the band is bending linearly, that means the field is constant, right? Okay. So this makes sense. I mean, field is constant means from Gauss law there is no charge. The moment you have charge, you have additional field or missing field. So the field, the charge causes nonlinear changes in the field, and then okay. So I think yeah.
Above the well.
Above the well meaning where?
Right.
Into the right.
Yeah.
But we found it, right? There's nothing left there, right? So you see, no, I mean, this is a good discussion. So let's see where did my buttons here go? Let's just check this. Oh, yeah, I had maximized it, of course. Yeah. All right. Yeah, I mean, we have integrated out everything here, and that's 2E12. There's nothing more. Yeah.
Flip back to the Venn diagram.
Yep. Oops, where is that? Yeah, there you go. Hi.
Is that whole structure actually charged? Because it looks like we have electric field on the left side.
Very good point, right? That's exactly right. Okay, so you see here there is a field, right? There's a field here. Band is bending. It's not flat. Band is bending. That means there's electric field. And if bending kind of linearly there. So and then you realize that what has happened here is, if we look to the left here, the band is bending. It's linear here. It's not curving. It's bending linearly, and it's curving here because there's charge. It's going linearly again because there's no charge there. Right? And the moment you have this here, you see there is a field in this region, okay? And the field is pointing in this direction. Because the way to think of it is, if I release an electron here, it's going to slide down in the conduction band. The field is pointing in that direction. And field started from positive charge, so that immediately tells you that there must be some charge on this side. So it's a misleading figure because we're not showing what's on the surface. The surface is typically a metal. It's a HEMT, so you have a gate metal here. Right? You have a gate metal here, and what has happened is the metal has become charged now, and the rest of the electrons, from 1e13 to E12 went here, 8e12 went to the metal. So there's a lever rule. Some electrons go here, some go there. Right? Okay, and that's the okay. So that's the resolution really. I mean that's where the electrons are. So now that tells you that after all this transfer and everything has happened, your band diagram and the charges and the fields will be connected in this way. So let's look at the charges. We have a positive ionized donors in this 5 nanometer of modulation dopant region. I have a mobile electron gas in the quantum well, and it's kind of like this, right? We just sketched that, and this can be large. And the rest of the charges are in the metal, and they are negative. So this is now your charge, and the electric fields. I think you can now sketch, let me just do that analysis now. And this is how we're going to calculate what should be the threshold voltage of this transistor. Yeah.
Wait, so how are those able to lead to the metal if you have that?
Yeah.
It's just, I guess it's not a big potential barrier to get. So can the electrons tunnel through? Is that other?
Yes. Okay. Good point. Okay. So let's look at it this way. The electrons in this, if they were sitting here, it would be a flat band, let's say, right? And the states would be here, right? And the idea to look at it is, if you're asking me the time dynamics, it may be a little tricky, but the equilibrium value is straightforward. Okay? Time dynamics would be, well, the moment you created this structure, you can imagine they were not together, but you put the three things together, a metal and the gallium arsenide on the right side. Just thought experiment. And these electrons are kind of ionized, so they are moving in both directions. They're thermally, they're in the band, so they're mobile. And so part of them go there, part of them go. But then as it happens, you can see that it will get harder because now the electrons have to climb up, right? Go there. But the thing about equilibrium is once you have equilibrium, in the end, the Fermi level has to be the same everywhere, right? So that will dictate what we got here. That's the end result of all that. It can tunnel. For example, what you can do is maybe shine. You have the structure sitting there. You can shine some light on it and put some more electrons here, excite from here, and then let it go. And it's going to go back. When you turn off the light, it's going to go back to this again. How? Well, it can either thermionically emit or tunnel or whatever. It may take some time, but it will go back there. Yeah, so that's the way to look at it. Okay, so you have a charge on the metal, but I think we all know that the charge in a metal cannot be spread out. It's always a sheet charge. Right? It's always on the surface of the metal. And this is from electrostatics. Because the conductivity of a metal is effectively infinite, it cannot support electric field inside, so there cannot be distributed charge inside a metal. It's always pushed to the surface, right? So therefore, the electrons in the metal are all on the surface. It's a sheet charge. Here's your dopant charge, and here's the mobile electron, 2D electron gas, and they must be all sum up to 0. That's what you're saying. And what we found, for example, here, 2E12, 8E12, and 1E13. So total sheet charges. We can simplify this problem a great deal by saying that I'm not really interested in looking at the 5 nanometer width. Maybe I'm going to just model this whole thing as a delta function too. And that's fine. You can do that. Just modeling it as a sheet charge is very convenient. And similarly, this one, I can model it also as a sheet charge. And that's going to be my Q times N sheet charge in the quantum well, Q times N in the metal, and Q times N dopant. Right? You can kind of break it up like that. Right? And that immediately you have a relationship between them now. But now going down here, you see in terms of electric fields, deep inside the metal, left side, the field is 0. Right? We're going to plot the electric field now. The field is 0. Then you hit a sheet charge, and this is, I think I did mention it when we're doing p-n junctions, but I'll mention it again. The field discontinuity across any region which has a sheet charge, let's say sigma, Q times sigma is the sheet charge density. The field discontinuity is just that divided by the dielectric constant of the insulator part of it. This is Gauss law. I think you may have done your electromagnetism course, you use some pillbox and all that, but if you have a sheet charge, no matter positive, negative, and the charge density is sigma per centimeter square, the field on the left minus the field on the right perpendicular to this region, the field jumps by this much. There's a jump. Why? Because Gauss law, if you remember, the field is an integral of the charge, and there's a delta function. You integrate it, you get a step function. So you get a discrete step in the field. So the field profile goes, whatever it is on the left side, and then it will jump like that, F1 to F2, where this difference is. And this is actually, in terms of just plain device design, it is one of the most useful and simple rules to remember. So as a result, you see that the field here, I have negative charge, and I have 0 field on the left, and when I go across the junction, the field is going to abruptly jump by Q times N in the metal over dielectric constant, not in the metal but in the semiconductor. It's always the insulator part of it. So that's the field that is in this region. Does that make sense? And you go across here, and then you hit this part, and there's another jump. Right? The field jumps again, but now it jumps the other way, right? Because now you have a positive charge, and it jumps up, right? And I think you realize that it has to jump, kind of higher than it has jumped here. The magnitude. Okay, so do you see it will be larger because this charge is larger than that? Right? So it will be larger. And let's just, for simplicity, look at it. Maybe look at it this way. So this is 2E12, that's 10E12, and that's 8E12, right? So roughly to scale now. And then the field remains constant because there's no charge here. And then when you reach here, the field kind of drops and goes back to 0 because the whole thing is charge neutral, right? This together is charge neutral. To the left is 0, to the right is 0, and this is the field, electric field distribution inside the whole structure. In reality, this part remains exactly like it is, but I think you can probably see that if I have a little thickness over which I have doped the region, it will not change abruptly. It will kind of go like that, maybe linearly, right, if it's constant doping. And then you go here, because you have quantum well, band offsets and all that stuff, you will kind of get a little broadening like that. And you can ask your 1D to plot that for you. It will do that, plot the field as well, and this is what you will get. So at 0 bias, when you don't apply any gate voltage and all that, the total area under the curve is what you would call as kind of the built-in voltage. So let me sketch out the band diagram now. So the band diagram, well, it's there. I think you can see now there's a band offset from the surface. This is the surface barrier height, Q times phi barrier, surface barrier height between the metal and the gas. And then we saw there's a constant field here. So the band diagram is such that you can kind of see right away that the net field is negative. So if I put an electron, it's going to move that way. So all that stuff. So and then kind of go up, drop here by the band offset, and then from that. It's not quite exactly accurate because this electron gas would be sort of centroid, would be kind of here, but I'm just not getting into all those details right now. It's very good for what we're arguing. And that's the band diagram you see there. Okay, so what I want to ask now is how does this charge depend on any questions about this, by the way? So we're going to look at this in some detail because one of the most important things about this device is, for example, what is the threshold voltage when I'm going to apply voltage on the metal and I have electron gas of 2e12 sheet density sitting here and I change the gate voltage. Let's look at it this way. Okay, so I think the charge figure is one of the best ways to look at it. So this is an 2D electron gas, and your transistor, for example, will have contacts to this electron gas, across this junction, one on this side, the other source and the drain, and then the gate is trying to control this charge now. Now, one of the questions is what is, for example, the threshold voltage, or sometimes also called as the pinch-off voltage, at which there is no charge left here. And that's kind of in quotes when I say no charge left. We'll see that there is more to that story, meaning, we're going to ask that. What is the pinch-off voltage of this device now? Okay. And then this you can say from this band diagram directly. I mean, this charge field picture in a very simple way. So you see, at least intuitively, that when I have this metal here and I have formed an ohmic contact to this electron gas, the structure looks exactly like this. Okay, so it looks just like this. So here's the gate. You have a barrier, electron gas here, and I formed ohmic contact. Do not worry about exactly all the details of this. I think we had discussed slightly last class that essentially you are connected to this electron gas without any voltage drops from the source and drain, negligible voltage drops. Okay. Now we are going to apply gate voltage and try to remove the electron gas. And I think it's very clear that you want to apply negative voltage to remove that electron gas, right? Right. And the question is how much? 0.2 volts, 0.5 volts, what determines that voltage, right? And that, I think you can see what will happen in the charge diagram when you apply the voltage. What's going to happen in the charge diagram? When I apply a negative voltage, maybe you can help me. What happens here when I apply negative voltage? Does this change? No. Ionized donors, they remain ionized. This doesn't seem to change, right? So all that will happen is this is mobile, that's mobile. The ratio of these will change. And as I apply more negative voltage, physically what am I doing? I'm putting more negative charge on the metal. Where is that negative charge coming from? It's coming from there. Right? Makes sense? So essentially, as you apply negative voltage, you shrink this down, 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 and you grow this by exactly the same amount. Right? Right? And then at some point, this will be very small, and I'll actually talk about that right now. And this will grow to a value which is essentially, you can see that when that happens, the field is going to change in a nice way. The field is going to increase here, and it's going to, do you see that the field is going to increase here because the discontinuity is exactly equal to this charge by epsilon. So this is going to increase, but then this difference between these 2 points cannot change. Why? Because this thing is not changing. Stuck, right? So the whole thing essentially just gets pushed down, and you can see right away that there will be a critical field or critical voltage at which the field in this region will vanish. It will go to 0, right? Because the whole thing is going down. At some point, the field here goes away. And you know that, how did that happen? Because there's no more charge left there. Okay? That's the pinch-off voltage. The voltage at which this happens, when this thing goes to 0 and this kind of, all the field drop is now here, that is the pinch-off voltage. It makes sense?
So you're moving the permeable terminal down or something?
Yes, that's right. So we're moving, basically what we're doing is we are connected with a gate voltage with a battery to the Fermi level of the metal, okay, and we are applying a voltage here, and the one I was discussing now is a negative voltage. So what's going on when I apply negative voltage is this is getting pushed up. We're going to sketch the band diagram now. Okay, let's look at this. So if the field is going up, you can see the band diagram. Let me resketch it. The band diagram was initially, something like this, right? The band diagram was something like that. But now I've pulled this thing up, in some sense. So I'm going to kind of, all of them have to respond correspondingly. Okay? So when I pull this up, let's say it is the dashed line now is the new band diagram. So, and the discontinuity across the field discontinuity is kind of going to remain the same. And I think you realize that this gets pulled up, but then the field here is vanished at threshold voltage or pinch-off voltage. So this is not quite accurate. When this thing kind of gets pulled up till here, you empty out the states. No more states left. Your minimum state has gone above the Fermi level now. And so in sketches, it's going to look something like this. This whole thing gets pulled up. And the so that voltage, wherever that happens, is your pinch-off or the threshold voltage. Right? Makes sense? So the entire field is confined in this region. No more field here, no more charge there. If there was charge here, there will be a field there too, because field originates and terminates on charges, right? So it's going to. So this is constant, and from here you can write down a relation between the carrier density as a function of the gate voltage that you apply here, and that let me just point that out, because that is kind of one of the things that is important here. Okay? Here's the picture. So you have a delta doping sheet here. Oh, by the way, so this if I shrink this dopant layer down to a very narrow region, that's what's called as a delta doping. It's just the name that has been used where so it's, if you shrink it down to a sheet, the dopants are only sitting in a sheet, and it's called a delta doping. So this is your delta dope layer, gate metal, barrier layer. So you go into the quantum well region, gas, 2 deg is sitting here. Here's the charge that I just mentioned. Remember, if you go, if you are on the other hand bending the band down, applying positive voltages, you can reach a situation when this little triangular thing can go below the Fermi level. I'm not talking about that right now. That's forward bias. Typically a HEMT, you don't want to take it into forward bias. It's operated in a reverse bias. It's called a normally on device. So that's why they have put a little N-par, means parasitic channel, NPAR here. It will form that if you take your Fermi, it will form there. But right now we're looking at reverse bias. So essentially all you need to do is find out at what gate voltage is the field here 0 or the voltage drop here 0, and you can kind of go around the loop and write it down. So you can start from 0 here, okay, go up by VG, go up by barrier height, phi b, drop by V1 here. What is the voltage drop here? It's the field times the thickness, right? Electric field. Here is just the charge in the metal is the field times the thickness of this layer is the voltage drop in that layer. So V1 is just, I've written that down, charge in metal times this distance here, d minus dm. Make sense? Yeah. Then you go back up by V2 plus V2, and that's again, this is not the pinch-off voltage, but for any gate voltage, this is the situation. That's what we're doing in general, right? So we go back up, and that charge with the voltage there would be just that, field times distance again, and then you reach there, and remember, you kind of go down and then you have to come back up to the Fermi level, and for that little window you use this EF minus E1 times m star by pi h bar squared, density of states times the energy bandwidth is equal to ns roughly. Okay. The next thing, because you started from the Fermi level of the substrate and you want to come back to the Fermi level of the substrate, so you got an equation, right? And the equation has only two unknowns. One is what is the sheet density here, and the other is what is the gate voltage here. This makes sense. There's only two unknowns. Everything else is known. The thicknesses, the band offsets, the barrier heights. These are all, once you choose your semiconductor, this is fixed. Right? Delta EC is fixed. Barrier height, if you choose your metal, is fixed. Doping, you control it. Where you put it, you control it. So all these are known. Only two unknowns are carrier density in the sheet density and the gate voltage. Right? So you got equation, solve it. Carrier density is a function of gate voltage. So this is how it changes. Right? Now this relation is approximate. It's typically meant for, as you know, first of all, it's not self-consistent, and we don't do Schrodinger. But the nice thing is you can see all the quantities here. There's a the little density of states and all that stuff appear and all that, but that's irrelevant. What is the pinch-off voltage? What's the threshold voltage when this is 0? Right, when ns is 0. So you put it equal to 0, you get a voltage. That's a pinch-off voltage, right? And you can see how it depends on the doping and the band offsets and barrier height. It's very, very clean and simple, and you can relate to that. Is that clear? Yeah. Now the simplest way to look at it is there's obviously the voltage divided by a capacitance voltage, or rather, if you want to deplete this much charge, you will always be depleting with some sort of a capacitance times the gate voltage, right? You'll be depleting because you're applying voltage, you're capacitively coupled to it. So if you look at this relation, the threshold voltage will be, on the right side, there will be a 1 over capacitance. With capacitance times voltage is charge. So, and the capacitance that appears here, if you forget about the band offsets and other details, is basically epsilon by d delta. Now that's your capacitance that appears. Dielectric constant of the semiconductor divided by d of delta. What is d of delta? Looking at this picture, it's basically the distance you put your delta doping layer from the surface. That's roughly the number. And you can see why. Because once you are pinched off, all the field is here, and what's going on the right side really doesn't matter anymore. Right? So this basically, it's just the extra voltage you have applied to pull the field down to 0 here. That is it. There's nothing else left. So does it make sense? So this is essentially a pinch of voltage, the area under the curve here, when this has been pulled down to 0, right? Is that clear? So if you now measure your electron gas density in the channel as a function of the gate voltage, what you would get is let's see, VGS as a carrier density in the channel, or Q times NS. At 0 gate voltage, there is we just saw 2E12 charge for the example we're looking at. And what I'm trying to say now is, as you apply negative voltage, it's kind of going to go down, and kind of merge with 0. And that's what we're calling as the pinch-off voltage or the threshold voltage. It's negative voltage here, the way because you started with some electrons in the channel already. Right? Is that okay? Yeah.
Should that be linear?
Okay, so from here you can see it looks linear, but it's an approximation, and it's a very good approximation once you have turned on that it will be linear. And the reason for that is because the density of states of a 2D system is constant, and your carrier density changes linearly with how far your energy goes from the minimum. That's why it's very close to linear, but things change quite a bit once you reach here. That goes, when it drops, it doesn't go to 0 at all, it exponentially drops. Because what happens then is the Fermi level goes into the band gap, and you have a little tail, and the carrier density is dropped exponentially. So let me just show that part of it, and we will take it from there. Gallium arsenide HEMT. Okay, so here's the band diagram we just saw. Here's the carrier density, and what you can do is set up the solver to do one more thing for you, and that's kind of a very nice a feature of this 1D Poisson program. is it will do what we call as capacitance voltage. It will calculate capacitance of the gate versus voltage. I have kind of disabled it here. I'm not going to run it now, but we can set it up. So basically, if you say that, well, I'm going to put the gate on the surface, here's my Schottky barrier height, 0.6 eV. 0.6 eV. That's what it's doing there. Or what I've chosen a metal which put on surface Schottky barrier 0.6 eV. Here's the structure we just talked about. Here's the modulation doping. And then the voltage on the surface that I showed you earlier is the equilibrium, no voltage on the gate. You can turn this off. You can turn this off and say that, well, I want to apply voltage now. I want to sweep the voltage from -1 to 0 volt at steps of 20 millivolts. Right? You can ask that, and it will basically show you two things: your capacitance versus gate voltage, which will actually, I'm going to sketch now, is going to look like that. The capacitance versus gate voltage, and the carrier density is an integral of this charge, is basically integral of CV. It's not exactly linear, but close. You can. So for design problems, it's linear is a very good approximation, and we kind of can go with that. Okay. So here's how it looks. Here's the capacitance for this junction. This is fully self-consistent. Now Schrodinger has been turned on. Everything is turned on. I mean, there's not much approximation left here. What it's showing here by looking at this, when you do a measurement, this is exactly what you see most of the time. You made the device correctly. I'll say that my pinch-off voltage for this device is -0.4 volts. That's the pinch-off voltage here, and then the capacitance is about 0.5, 0.6, or 0.7 microfarad per centimeter square. And what is that capacitance? It's exactly what I wrote here. If you plug in, epsilon is about 11 for gallium arsenide times your 8.85 times 10 to the power minus 14 farad per centimeter. Distance, we chose what, like 3 nanometer, 30 angstroms on the surface or something like that. 3 nanometer. Use the right units, you will get 0.7 microfarad per centimeter squared. So when you do a measurement, it immediately tells you you have done a growth. You don't know exactly. You have planned to have 5 nanometers here or 10 nanometers here, but you don't know exactly what has happened. You make this measurement, and you right away know what is this d delta now. Kind of interesting way to measure it after you're all done. Does that make sense? Thus the capacitance, when it flattens out, it's kind of called the zero bias capacitance. And the carrier density, as I was mentioning, is here. So this is plotted in 10 to the power 10 per centimeter squared. So at -0.4 volt, you're pinched off, but then you start roughly linearly. It's not exactly linear, but roughly linearly. And then at about 0 volt, you reach about 1.2 E12 per centimeter square for this particular simulation I have done. So it's 10 to the power 10, so 120 times 10 to the power 10 is 10 to the power 12 per centimeter square, roughly. Okay? But if you zoom in into this part where it's turning off, that's where if you are actually doing this in 1D Poisson, it might complain in terms of convergence, because it has to deal with very small numbers, 10 to the power minus some 12 and 11, but it drops exponentially below 0.2. So, and that's because the Fermi level is going into the band gap, and you have a little tail left, and this is the amount of electrons that's left over in the band. So it's a little tail of electrons that's left over in the bands. When you are in this situation, you had a lot of electrons, but now you have a very tiny tail. It's exponential decay. So that's when, if you look at the transistor, when it's switching off, you measure. So that is actually a measure of the Fermi-Dirac distribution of electrons in the band. So it's called the sub-threshold characteristics of the device. Okay. So questions on this? And I will give you a problem for you to practice this particular aspect of the story, but and it's kind of very useful to look at CVs and carrier density. You can draw the band diagram. So just as a 1D Poisson, this particular program does very well if you apply reverse bias. Forward bias, it doesn't like it very much. Because basically what happens in reality is when you forward bias this and you pull it down, your current turns on. It's a Schottky diode. Your current kind of turns on. And 1D Poisson is not meant for transport. It's meant for electrostatics primarily, near equilibrium situations, and or when you're pinching it off. But on states, it doesn't, doesn't like that, but there's a limitation of this program. There are obviously a lot of other programs which you can see what happens. Okay, so now what we are going to do is spend the last 10-15 minutes today talking about the same thing, but in gallium nitride material system instead of gallium arsenide, and then this will help us to look at a few specifics of this not new but relatively new material system, and let's look at this particular material system and see how what we talked about change. How do these things that we just discussed today, HEMT, threshold voltages, charges, how do they change in a nitride system? So gallium nitride and aluminum nitride and indium nitride, that's the 3,5 compound semiconductor nitride family. This material, this crystal is gallium nitride can crystallize in wurtzite or in traditional zinc blende too, but zinc blende is thermodynamically very unstable, and I think in the later half after the break we are going to look at that material science. Why is one phase better than the other and all this. But right now let's accept the fact that people have tried to grow cubic GaN for a long time. Some have had some success, but it's generally thermodynamically very unstable. It's metastable, that's what the right word. But we're going to look at the wurtzite part, and how is the wurtzite part different from all the other semiconductors that we have talked about, gallium arsenide, even silicon. So this family is called the zinc blende. I think you know that part, right? It's basically the same as the diamond or the silicon structure. It's just that the nearest neighbors are different atoms. It's compound, right? Gallium and arsenic, or indium and arsenic. So all these are zinc blende, and the crystal structure looks like this. Let's think this is gallium, and the reddish one here is arsenic. So if you go up to the next level, so essentially this tetrahedron, this atom is right on top of that one, right on top of that one. And then it keeps repeating along this 1-1-1 direction. Does it make sense? So this is gallium arsenic, but the arsenic is right, in 3D space. You can think it's right on top of that z-axis. Wurtzite is just slightly different. You go up, and there's a 60-degree rotation, in the next step. So is one tetrahedron like that. You go up, the next tetrahedron is not right on top, but it's just rotated by 60 degrees. Okay. So, did I say that right? Yeah, that's right. So and that's kind of the major difference. And as a result, you see, this structure has what you call cubic symmetry. So if you go this way, and you can show that if you go this way or the x, y, z axis, it all looks the same. But here it looks very different if you go in this direction than that direction. So this 60-degree rotation is only along that direction, not in the other two. So this is called a uniaxial crystal. So it has a lattice constant that is slightly larger in this direction, c axis, about 5 angstrom. In this direction and that direction, x, y, it is about 3 angstrom. So it's a hexagonal crystal, so longer in one direction. It's basically kind of, you can think of the stacking is kind of twice in one direction than the other. I say okay, that's the way to look at it at this point. But the major differences in electronic properties, first things first, is the band gaps are generally quite a bit larger. Gallium nitride is 3.4 electron volts, aluminum nitride 6.2 electron volts. Indium nitride is actually kind of small, 0.7 or 0.6 eV. There was a big controversy with the band gap of indium nitride. Till 2001, everybody thought indium nitride band gap was 1.8 electron volt. And the reason for that is people grew the material. It's a very difficult material to grow. The crystal growth is difficult. But whenever they grow it, and they do an optical absorption band edge measurement, they always say it's 1.8 eV. Till 2000, and when people first grew it by high MBE, very good control, growth technique improved quite a bit. So that happened actually almost simultaneously, one in IOFI Institute in Russia, and the second here in Philips Hall by Bill Schaff. And when they did the measurement of this, they measured about 0.7 electron eV. And the reason it was people were measuring these very large band gaps is basically it was so defective, earlier. So the real band gap is about 0.7 eV, the best we know today. But it was so defective, and it was highly n-type. So the Fermi level used to be kind of very deep in the conduction band. And then when you do absorption edge measurement, your excitation edge is kind of this much. It's not the band gap, so you kind of get a blue shift called a Moss-Bernstein shift and all that. Anyway, end result, most people believe today, and we have also done quite a bit of those measurements now. We think it's 0.7 eV. The better it gets, the closer it gets to 0.7. In fact, it's getting closer to 0.6 now, because but still very defective. It's very difficult material to grow. All right, let's look at GaN though. Okay. Gallium nitride, most important things, quartzite, different from cubic. They're all direct band gap. So the minimum of valence, minimum of conduction band and maximum valence band are the same point in K space. Right? That we have talked about earlier, direct band gap, and that's the reason they are very efficient light emitters, and so are gallium arsenide and indium phosphide and all that. I mean, so they are also direct gap. The ones with the black dots here, not the ones. Open circles are indirect gap. Black dots are direct gap. And these also are efficient light emitters, and these are also efficient light emitters. It turns out that in addition to being very efficient light emitters, the nitrides are also very robust, meaning the light emission process, because of a confluence of many intended and unintended reasons, it is very difficult for this material not to emit light. It just wants to emit light, even in the presence of defects and all that stuff. So one of the important properties of the nitrides, which is why it's been now the framework for all LED and laser, a lot of solid state lighting and that. Yeah.
I just have a quick, they haven't done like ab initio calculations on the band gap of...
Yes. Yes, they had. I will just tell you the truth, without any emotions there. Till 2000, the ab initio calculations said that the band gap is 1.8 eV. And in 2003, they said it's 0.7 eV. So that's all I want to say. And it has been well accepted now. So yeah. I'm not disparaging anything. It is a very good example that the theory is based on assumptions, right? And then you add it and make it more and more accurate, and then it tells you different stories. So that is the truth. Like, you can track back the papers, and that's what happened. People got into fights about the band gap in conferences. I mean, not verbal, but almost physical. So because it's actually a very big deal, right? I mean, once you get down here, you're getting into infrared and getting into almost communication wavelengths. Yeah? So I don't think this is true, but people get worried because you have a whole industry based on communication, lasers, and all that here, and you have suddenly a new material that is already creating lighting and all that. Maybe it will also replace all this stuff. So there are some stakes there that people don't want to let go. Anyway, yeah. And then there's the fundamental science of it, because if you strongly believe it should be 1.8 eV and somebody tells you experimentally, no, it's not, it's a little troublesome. But, yeah. Science doesn't care about human emotions, but yeah. So, all right. Okay, so band gaps range from basically infrared all the way to deep ultraviolet, and visible is somewhere around here. So one of the interesting properties pertaining to what we are discussing now is the fact that the nitrides, because they are uniaxial, they have very strong polarization fields. And I hoped I was hoping I had a bit more time today, but that's fine. So it has a very strong polarization field, and let me explain first what that means. So polarization of a crystal is, so the nitrogen atom. I think we have seen this. Let's just look at the periodic table. You have beryllium boron. So okay, nitrogen, oxygen, and then you have aluminum, gallium, and all that, right? Indium, carbon. What's there? Silicon. I'm just going to fill this up because what you see is the trend. Phosphorus, arsenic, antimony, right? So nitrogen is sitting right on the top of the group 5, right? This is group 5, group 3, and we're looking at the 3,5 semiconductor, gallium nitride, aluminum nitride, indium nitride. And very soon there is going to be it's quite a bit of interest in looking at boron nitride as a compound semiconductor counterpart of carbon or diamond in 3D. We already talked about 2D boron nitride in the beginning, but I'm talking about 3D boron nitride. Anyway, right now. So nitrogen is the lightest group 5 element, and it's also the most electronegative among all. So it basically, whenever you have a bond between, say, a gallium and, say, an arsenic atom, or you have a bond between gallium and a nitrogen atom, these bonds are very inequivalent, in some sense. So arsenic has very, relatively lower electronegativity. It's not as electronegative. So it will, but it is more electronegative than gallium. So it wants to pull away the electrons from gallium. So when we form a bond. So if you were to sketch the electron cloud, it will be, maybe something like that, and this will be a little bigger, and so effectively, it's slightly polar. But this thing is very polar, meaning nitrogen basically sucks out the entire electron cloud towards itself. It's very polar. The charge electron cloud is mostly near nitrogen. So if you look at it from a point charge perspective, this is kind of slightly positive charge, this slightly negatively charged. So there's a dipole. Every compound semiconductor has a little dipole in the bond. It's a covalent bond, but there is slight amount of ionicity to it because of difference of electronegativities, and that thing is amplified a great deal here. It says this bond is very unequal. It's not really an ionic solid, but at the verge, it becomes very ionic, so very polar. So the bond, you can imagine, is it's positive charge, negative charge, and so you form a dipole here. So every bond, chemical bond, you can imagine it to be a dipole between every gallium and nitrogen atom is a dipole. You can think of it that way. This is a classical way of thinking about the problem. There's a more accurate quantum mechanical way of thinking about it as well, but I don't want to get into that aspect in this class. Okay? So there's these dipoles, and then now the picture of the dipoles is the following. You take the crystal of gallium and nitrogen, gallium nitride. Let's look at this one, gallium nitride. It's crystal, and we're going along a certain axis. This is the uniaxial direction, not the cubic, but it's hexagonal, and this is the along that direction, the crystal structure looks, rather the geometry of the crystal is is hexagonal. This is c-axis. Lattice constant is about 5.1 angstrom for gallium nitride. Here, lattice constant in the xy plane is about 3.1 angstrom, or 3 point something, forget. Okay? And that's called A. Okay? And this is C. This is the vertical. So you have kind of these dipoles in every chemical bond, and then so you can think of it as the nitrogen is slightly negative charge, gallium is slightly positive charge, and this is the little dipole arrow schematically, and then right. So now you see that if you had dipoles in every chemical bond, and every atom is bonded to 4 others, right? Nearest neighbors. Gallium is 4 nearest neighbor, nitrogen is 4 nearest neighbor, gallium. And if your packing of the atoms were exactly, when you pack hexagonally, so you have a C over A, the ideal C over A ratio, if you pack basically balls of same radii, okay, exactly the same radii. This is, of course, it's a geometry problem. If you pack balls of the same radii, this way, and then another one this way, another one this way, and then another one this way. This is the period. So this is typically a period of a lattice. So you'll see that the C over A, which is the lateral lattice constant, is all related to the radii geometrically. For ideal packing, it should be square root of 8/3. If you have ideally stacked them in the right, with the same radii. If that is true, if that were the case, then all the 4 dipoles form the. So in a way, the way to look at it is you have this is a tetrahedron, all right, and the gallium atom, let's say, sitting inside in the middle, which is the centroid of the tetrahedron, if it is ideal, right? And there is a dipole pointing that way, that way, that way, that way, and you vector sum these 4 dipoles, right? You get a 0. Right? I mean, that's the meaning of the centroid, right? You get a 0. And this is true if it is a cubic crystal. If it's a cubic crystal, it's true. If it's a word-side crystal with C over A, it's also true. If C over A is exactly square root of 8/3, these 4 dipoles will add up to 0, even in a word-side crystal. Right? But in the nitrides, what happens if you do the crystal structure, if you grow the structure and you do a very careful TEM, X-ray measurement, and all that, what you notice is actually C over A is not square root of 8/3. That symmetry is broken. I mean, that it's slightly less. The C is slightly less than this ideal structure, and as a result, there is a slight deformation of this dipole. You can see this cancellation of 4 dipoles is a very delicate matter. It assumes perfect symmetry, and it turns out this crystal is not quite, C over A is not quite square root of 8/3. It's got to do with gallium and nitrogen, obviously have different radii, etc., and that sort of thing. But this is As a result, what happens is because of this thing, these 4 dipoles really don't add. There's a slight deformation, and you get a net dipole in every tetrahedron now. The net charge dipole in every tetrahedron, and that is the origin of what you call a spontaneous polarization in gallium nitride. If you've done some other material science, you realize there's ferroelectricity, which has a dipole in every unit cell of atomic charge density, electron charge density. Here, it's kind of like that, except this thing is frozen. You know, if you grow a crystal in this direction, the direction of the dipole is not changing. You cannot turn it around. You cannot turn it around. It's frozen, and as a result, you can think of this crystal now of gallium nitride as many of these unit cells. Every unit cell is distance c, and inside every unit cell, you have these dipoles, right? Like that, and there's another dipole like that, an array of them laterally, right? And you join all the tips and the tails of them, right? What does it look in terms of charges? Charges looks like, well, I have a positive sheet charge here, and a negative sheet charge there, and a positive sheet charge here, and a negative sheet charge. So it's kind of going back and forth, right? You see that sheet charge is repeating, right? And every plane only in that perpendicular to that c direction. Calculate what is that sheet charge, 10 to the power 13 per centimeter square. Right? Remember, these charges are not charges in the bands. These are just because that electron cloud got deformed, and you kind of saying a little heavier weight here, a little lighter weight there, slightly positively charged, slightly negatively charged compared to uniform density. That's all there is. This is not mobile charge. It's fixed charge. The density of the order of 10 to the power 13 per centimeter square, and what we'll see, I think we are out of time today, but basically you can see right away that if I have this sort of a high charge density, it will create huge fields internally. And this thing is actually, I haven't even doped it yet. This is just a nitride semiconductor without doping. Already there's a huge internal field, and that is the key difference between the nitrides and many. Basically the bands start bending even if you haven't done anything inside the material. And then you use this in a very clever way to make heterostructures, and we look at the gallium nitride HEMT. What happens at heterojunctions is there's a discontinuity in the and you get a sheet charge, and essentially it will kind of the main point is because of this property, gallium nitride has a lot of spontaneous polarization even when you don't strain it, and the spontaneous polarization is about an order of magnitude lower than ferroelectrics. Ferroelectrics, this charge is, I said 10 to the power 13. Every atom contributes to a charge in ferroelectrics. It's about 10 to 100 times stronger in ferroelectrics. But in ferroelectrics, the major difference is you can flip it. You know, you can have domains where some dipoles are this way, some dipoles are that way. You know, ferroelectric nitrides, they're all in one direction. So that's, you cannot flip it with external fields, and then yeah. So that's the spontaneous polarization, and then when you strain it, you get piezoelectric, and we'll talk about that in the next class. All right. Okay.